Differential Equations, Section 3, Numerical Solutions. Video 3, the Modified Euler Method. In the previous videos, we've seen how we can use the Euler method to estimate approximations to a differential equation. Now, the problem with the Euler method is that it assumes that there'll be the same gradient across the range, and so we can start to get away from where the actual solution curve would be. But there's a modification we can do that will make it a little bit more accurate. So let's have a look at that. So here's our diagram with our solution curve and our point on the curve xn, yn, and for the Euler method we assumed that the tangent at that point would remain constant in order to approximate the right-hand end. So our approximation favours the left-hand end of the interval because it's assuming that the gradient at the left-hand end is what's going to determine the behaviour. If we could find the gradient at the right-hand end as well and find the average, then that would give us a gradient that was somewhere in between what happened over the interval, and it would be a better approximation. The problem is we don't know the point on the solution curve at the right-hand end, but we can approximate it, and that's how the modified Euler method works. So we know that the tangent at the left-hand end is f of xn and yn. Then for the right-hand end of the gradient, we don't know what this point actually is going to be, so we use the approximation to the point, which was to have my x-coordinate as xn plus h and my y-coordinate to be yn plus h times f of xn yn. And then what I do is I say, well, let's use these in my gradient function f, and that will give me an approximation to the gradient at the right-hand end. And then by finding the mean of the two gradients, I get something to approximate what the gradient might be over the course of the whole interval. So the mean of the two gradients is a half times f of xn yn, that's the left-hand gradient, plus f of xn plus h, yn plus h times f of xn yn. That's my approximation for the gradient at the right-hand end of the interval. Now this is quite a lot to program into our spreadsheet. So this is our new estimate for the y-coordinate on the right-hand end of the step. We've got our yn plus 1 equals yn plus, and then it is this average gradient, h over 2 times f of xn yn plus f of xn plus h, yn plus h f of xn yn. It's a mouthful to say, it's even more of a mouthful to type. So what we do is, instead of trying to do it all in one go, we use some extra values k along the way. So notice that f of xn yn appears here, but it also appears here. So having something in terms of h times f of xn yn is going to be useful. So I define k1 be h times f of xn yn. Then my k2 is given as h times f of xn plus h, that's this bit here, and then yn plus k1, yn plus hf of xn yn. And then to put it all together into my formula, yn plus 1 is yn plus a half of k1 plus k2. So k1 and k2 are being averaged out here. Now in the next video we'll work through an example of this using a spreadsheet to show how the modified Euler method can be used in practice. In this video you've learned how to modify the Euler method by considering the average gradient.